Howdy! We are going to continue our unit on polynomials by getting into some more multiplying. And this time we're going to multiply polynomials. And we're going to do it by using the method that we introduced in the last lesson that talked about modeling multiplication. So a quick review on what we talked about last lessons to make sure that we're on the same page with our vocabulary. If you remember, we talked about multiplication in two different ways. The first is as grouping equal amounts by what we have learned pretty much since kindergarten. So that's what multiplication is. And the second thing we learned that multiplication is about expanding dimensions. And we talked about how we can take the addition of units and it stays in that same dimension. So inches and inches stays in inches. However, if we multiply those units, we now are working in a completely different dimension. So if we multiply inches by inches, now we're dealing with area and we're dealing in square inches. And so we use that to talk about multiplication. And we're going to expand on this area model. So we know multiplication deals with area, and we can use then area to model multiplication. And so I'm going to talk about modeling area with multiplication, and we'll see how that applies. If you remember, area of a rectangle, of course, just like the previous lesson, is length times width. So we have our most basic example, a tiny little rectangle that is 3 inches by 7 inches. The area of that rectangle, of course, is 3 times 7, or 21 square inches. In case you remember, we talked about how multiplication increases dimensions. So inches times inches, square inches. Okay, so now we're dealing in area. Now, the same method can be applied to multiplying some significantly larger numbers. And so if we had a simple multiplication fact to work out, 27 times 56, we can then use area to model that process. But if we're going to use area, we also have to use place value. Okay, so we can use area and place value. So take a look. If we have 27 as one of the dimensions, so 27 then can be looked at in place value as 2 tens and 7 ones. And since we're multiplying these two, we're going to use the area model. So I'm multiplying 2 tens and 7 ones times 56. And of course, 56 is 5 tens and 6 ones. Okay, so what's happening now is I am multiplying these two lengths in terms of an area model. So I have an entire area, but now I'm looking in terms of 4 tiny rectangles. So 4 smaller rectangles will then add to give me the entire area. So our first rectangle, of course, 50 times 20, 1,000. Our second rectangle, 50 times 7, or 350. Another rectangle, 6 times 20, or 120. And then our last rectangle, 6 times 7, or 42. And so I have the area of each individual rectangle using multiplication and using that area model. So the area of the larger picture at hand, 27 times 56, is all of those areas combined, okay, or 1512. And so we can then use that model with area and place value to apply it to anything with multiplication. So with our first expression with multiplying polynomials, I want to use that model, but I want to use algebra tiles. Okay, so we're going to set up a rectangle with this first example, x plus 5 and 2x minus 3. We're going to use rectangles and algebra tiles. So the first dimension, x plus 5, can be modeled with, of course, our x tile and 5 unit squares. Okay, so if you remember, we had our 5 unit squares. And so now we are looking at one length that is x plus 5. Our second length is 2x minus 3. And since we're multiplying them, we can use the area model. And so we're looking at 2x's, right? So our 2x's, and then 3 negative 1s. And so we are now looking at an area model. Okay, so what we can then do is start to use area to fill in gaps. So if we look at just this x here and this x here, we're thinking, well, what is x times x? Of course, that is x squared. So let's keep that nice and organized. All right, so we have x squared. And again, we have this x times this x to find the area of this rectangle. And that, again, is x squared. And now we start looking at those the bottom rectangles. We have a -1 times an x. Right? So -1 times x is going to leave us with a -x. And then we do that 2 other times. -1 times x, -x. -1 times x, -x. Okay, so we have modeled that. Pardon this interruption about to come.
John Ortiz, please come to student services, please.
All right.
John, please come to student services.
Thank you for the interruption. So we're going to continue with that same type of modeling. All right, so now we have more rectangles here. We have an x times a 1, which is a positive x. And then an x times a 1, again, a positive x. And we do that until we have mapped out this x times those 5 ones. So we'll do the same thing on the bottom row. This x times all of those positive ones. All of these are now positive x's. Okay, so we fill in our tiles. And so we have our algebra tiles here. And now we have this little bottom corner down there. And what are we going to fill that in? Well, we have our area model. So we have this -1 on the side, right? So this -1 times this +1, right? So a negative times a positive, of course, is negative. So all of these bottom spaces are going to be filled with -1s because all of them are -1 times +1. And so we fill in our spaces, and we're going to look at the rectangle as a whole. And so we now consider all of the pieces that make this giant rectangle that we just filled in. Okay, so we have all these little rectangles making a giant rectangle as modeled by our previous work with 27 times 56. All right, so we've made our rectangle. Now what we no longer need are the dimensions that we started with, so we can kind of brush those away. And here is our giant rectangle, right? So this is everything that we had added together. And so since we're gathering all this together, we look for zeros. Since we're gathering together, we look for zeros. We can take our 3 negative x's and 3 positive x's and get rid of our zeros. And that's it for the zeros. What is it that we have remaining in our model? We have 2x squareds. We have 1, 2, 3, 4, 5, 6, 7 x's. And we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15 negative 1s. Excuse me. So when we use algebra tiles, the area model, and we multiply these two polynomials, we can see that our resulting expression is going to be 2x squareds plus 7x minus 15. And that's how we can approach problem or the expression number 1. That's one of the ways. I'm going to show you a couple other ways. So what if you don't feel like playing with these algebra tiles? You can still set up an area model, right? We can still look at x plus 5 as a length, and we can still look at 2x minus 3 as a width, and still consider units of measurement, still consider place value, right? So how many x's in x plus 5? We have this length, which is x, and then this length, which is 5 ones. And that is x plus 5. And here we have 2x minus 3, so we can have this length, which is 2x, and then this length, which is actually composed of minus 3's. Okay, so we're modeling again using area multiplication. So what we have just made now are 4 rectangles. And with our 4 rectangles, all we have to do is find the area of each one and add them all up. So we find the area of that first rectangle. We have 2x times x, or 2x squared. In this rectangle here, we have 2x times 5, or positive 10x. In this rectangle down here, we have negative 3 times x, or negative 3x. And in our last rectangle, negative 3 times 5, or negative 15. all we have to do now is look for anything that has the same units, our like terms. And as you can see, we have x's and x's. So we can completely combine them. So we'd be left with 2x squared, 10x minus 3x is positive 7x, and then our 1's at negative 15. So again, no matter what, 2x squared plus 7x minus 15. That's another way to approach that same principle. Our last approach is going to be the distributive property. Okay, so now we can approach number 1 using the distributive property. Now, how do we use the distributive property? Remember what the distributive property does. It multiplies one thing through a group. We talked about this in the last lesson. We can multiply through. Right? So that means we can take x plus 5, what we have there, and multiply it through times 2x, and then x plus 5 times negative 3. Exactly the same way we approached multiplication in the previous lesson. And we could just use the distributive property twice. X plus 5 times 2x, of course, 2x squared plus 10x. And then x times negative 3 minus 3x. And then 5 times negative 3 minus 15. So now we have this little expression that we can, again, combine like terms. Plus 10x minus 3x. We can combine those terms. 2x squared plus 7x minus 15. And the other method, I don't like the acronym FOIL. I really don't. Because it only applies to two binomials. What I have shown you thus far applies to absolutely anything. The last method, that FOIL method, I don't like because FOIL only applies to binomials. And I don't like that. I don't like restrictive processes. So I'm not going to use that. Okay, so if you want to continue using FOIL, just remember that it only applies to binomials, and I don't like it. Okay, so if you're looking at the distributive property, I'm cool. If you're looking in terms of FOIL, make sure you're applying it only to binomials. And so that way you don't miss anything. So I would strongly recommend you stick with other methods. And now we can use those same processes for number 2, 3, and 4 that we can rock out real quickly now. So we know the expression for number 1. So what about number 2? You know what I want to do? I want to use the area method real quick. And I think that'll show some neat stuff. So if we use the area method, I'm simply multiplying the length, x squared minus 6x plus 2, times the width, 3x minus 1. It doesn't matter which way. But we break it down with place value. X squared is made up of, well, an x squared, and then we have a minus 6x, and then a 2, and then 3x minus 1. Well, of course, there's 3x here and a minus 1 here. And now we have our rectangles set up and ready to go. So if we use our area model, what you may have referred to as the lattice method previously for whatever classes you use that with. Now we find our areas. 3x times x squared, of course, is 3x to the third. Excuse me. 3x times negative 6x, negative 18x squared, 6x in that last rectangle up there. Now for our bottom rectangles, negative 1 times x squared is negative x squared. Negative 1 times negative 6x, positive 6x. And negative 1 times 2, negative 2. And now we look for our like terms. We have x squareds here and x squareds here, x's here and x's here, and we can just combine our like terms. So the first thing we have is 3x to the third power. Then we have negative 18x squared minus x squared is negative 19x squared. And then we have 6x, and 6x is 12x, and then minus 2. And we have now used the area model for that same expression. I can also use the distributive property model. And so that's how I'm going to show the next one. So 3x minus 1, x squared minus 6x plus 2. And now I'm going to use the distributive property model. And again, this is what you're about to see is not FOIL. My goodness. Okay, so please don't call this FOIL because it isn't. The first thing I'm going to do is multiply 3x times x squared, which gives me 3x to the third power. 3x times minus 6x is minus 18x squared. See, it's the same thing we just did, but with a different look. All right, and that's my top line, if you want to call it that. Now we have minus x squared. And then for the minus x squared, I'm going to line it up underneath here, right? Because it's going to be easier. And then plus 6x, wrong color. And then a minus 2. And so I have my two multiplication methods there. And now I can just add straight down. And if I add straight down, I'll have my simplified version. 3x to the third power, negative 18 minus 1 is negative 19x squared. 6 and 6 is 12 plus 12x. Minus 2, done. Okay, so that would then be, no matter which way we look at it, either area model or distributive property, you're going to end up with the same result as long as you're doing things right and being careful with signs. All right, so number 3, choose your method. It doesn't matter to me. I like the area method, so I'll stick with that. So we have x squared minus 4x minus 5. Just for space sake, I like putting it here. So there's my x squared. There's my minus 4x. There's my minus 5. And then my 2x squared plus 3. So 2x squared and 3. So here's my area model set up and ready to go. Now 2x squared times x squared. 2x to the fourth minus 8x to the third minus 10x squared. 3x squared here minus 12x and minus 15. Right? Now just I'm looking for like terms. And the only like terms I have are simply these two. And the like terms are easy to see here in this method. Like terms are easier to see here. So my resulting expression is only this much. Because that's it for like terms. So this is my resulting expression. Okay? And if you want to use the distributive property method on that as well, you can. Okay? Nothing wrong with that. And then lastly, number 4. You know what? For this one, I'll use the distributive property. Why not? So what we have to do, remember that example of foot-pounds that exist. Remember, we can multiply units. We can multiply units. So there is such thing as that. So the first thing I'll multiply is 2x squared times 4x squared, or 8x to the fourth. And then 2x squared times y, 2x squared y. And then minus 3y plus 4x squared, so that would be negative 12x squared y. Then minus 3y squared. And now I can combine my like terms in the middle, and I'm all set to go. So it doesn't matter how. Even if you were to use the area model, you would get the same result. I guarantee it. And that is how we multiply polynomials. And this applies to any polynomial whatsoever. Because remember, we are using area and place value. Okay, so if we use area and place value, we are good to go. Hope you enjoyed that and learned something. I will see you on the flip side.